Good morning. This is Engineer Suraj Singh from Bharat. I'm a professional engineer civil. I was involved in sharing with you guys about the civil engineering buildings practice, and I had given many videos on that, about 9, and one video I gave about soil investigation. This video is in continuation to that soil investigation number 2, and because soil investigation is very important for a civil engineer from the consideration of foundation designs. Foundation designs is a very complicated subject, and it's very complicated as far as the calculations are concerned, and yet it's not clearly known to the human being. To the engineering world, it's not clear from the engineering point of view. It is clear from many other disciplines point of view. So to continue, I should like to discuss or share with you people applied geology. Applied geology, that is a subject in itself. It's a big subject. It's a part of geology. Before knowing that, what is geology? Geology is the science of earth. To know the scientific, to do scientific study of the earth structure. Earth. But what is earth first of all? Earth is made up of two components. One is the earth which we are calling this earth, but air is also included with earth. Earth means lithosphere. This solid portion, we call it lithosphere, while the air envelope, which is about 18 to 20 kilometers surrounding the sphere earth, this lithosphere, the lithosphere plus aerosphere is called earth. And in the subject, within the domain of the subject, applied geology, this is spherical, two spherical words, lithosphere and aerosphere, are to be studied, and these are usually studied. You can say most of the portions of geology or applied geology constitute the study of lithosphere. Lithosphere, which is considered about 12,500 kilometer diameter ball, a sphere, we call it ball, a globe, and first 35 kilometers of this ball is called the crust, which contains generally soil and rocks, seas, oceans in this crust. While if you go further to 2,000 kilometers, it is called the mantle, and further down to 6,000 kilometers is called the core. Most of the Earth's activities happen within the layer of crust, that is 35 kilometers, and also within 2,500 kilometers. The real nature of the constituents composition of core of the lithosphere are yet unknown, not clearly known. Its high density composition, while in the mantle it's medium density composition, and crust is low density composition. I am calling low density in the sense, for example, if you take the density of a rock cube, it won't exceed more than 2,500. But in mantle and in core, it may be 8,000 or something. That is unknown yet. Well, to start with and to continue this, I'll concentrate on crust, because most of the activities that we deal with relate to crust portion, crust of the lithosphere. This crust, 35 kilometers, is very important because building foundations rest on the soil of this crust. Aerosphere is another discipline from engineering study point of view, but now we will concentrate on crust. Crust has got, before that I'll take you to oceans and seas. Seas are generally up to 10 kilometers average, while oceans are up to 12 or 13. Seas could vary from 4 to 10 kilometers, and rocks below the sea, water, are generally basaltic in nature, while other areas, continental areas, have varying stratification of rocks. Actually, whole earth is rock. These rock particles break, and there are so many energy release and energy development within the crust and within the mantle and within the core. These are very high level, high magnitude energies which when are released to get back to the equilibrium of energy world, you can say there is vibration within the earth and earthquakes are generated, seismic actions are generated by the development of primary and secondary waves. Well, that is not the issue here for discussion. So I'll take back to our discussion of crust. Now, what is rock? Whole earth is considered rock. Rock means there are 2 or 3 types of major rocks. One rock is igneous rocks. Igneous means which is formed by the existence of or by the revelation of energy in the form of fire. That is volcano. There is magma below the ground, and when it is erupted out onto the surface of the earth, it is called volcano. Volcano means crater of the volcano, that is fire you have seen on the earth. This is igneous rocks. While there is another kind of rock which is constituted by the process of sedimentation or settlement of the earth particles due to wind erosion or due to any other reason. Wind erosion is most responsible for the light particles. Due to heavy winds, the particles in huge quantities fly, travel in air and precipitate at another location. And this process continues for years and years and years and millions of years while you see the layers are sedimented. These are called sedimentary rocks. For example, limestone or sandstone. These are results of consolidation and settlement of various such flown away particles of rocks. This is sedimentary rock, we call it, by the layers. When there are various layers, you say many layers are sedimented and give the name sedimentary rocks. Whereas if you see on the sedimentary rocks, there is imposition of weather. There is imposition of cold weather, hot weather, various kinds of gases and chemicals impart adverse effect onto the sedimentary rocks, and by the time passes, these sedimentary rocks are worked upon by these chemicals, and these chemicals transform the real crystallization of the rocks, and they transfer to another name which is called metamorphic rocks. So sedimentary rocks, and the third is metamorphic rocks. Now we take, for example, what types of soil are there. We can say, based on igneous rocks, due to erosion and due to many other reasons, you will find granite, you will find basalts. These are the products, but these are very strong rocks, volcanic rocks. Rock is very important from geological viewpoint. Rocks, and then there are gravels, pebbles, sand, clay, silt. These are various classes of soils. From engineering point of view, the rock is rock. There is no second opinion on that. But this is very solid rock. This does not integrate very easily. This igneous, Agni in Hindi we call it, igneous. While the other nature of rocks like sedimentary rocks, which disintegrate into sands, fine sand or coarse sand, dune sand, and then further to very, very fine particles like clay and silt. In organic clay, silt. Clay and silt is a different world. Clay, which you call in Hindi chikne mitti, Clay is used for tiles making. It's used for pitches. It's used for refractory material, clay blanketing. It is also used for flooring in villages. It's used for walls, plastering, and for many other purposes. Here, the purpose is we should know the properties, the behavior, the conduct of all these various types of soils. Here we call rock also a part of soil because rock is the name, but it's a word of soil. Rock is the top one, igneous number one, then then sedimentary, and sedimentary is little weaker than clear rock of igneous, because if igneous is faulty or weak planes are there, it may be weaker, but sandstone or other stones are also stronger for the purpose of engineering consideration, while metamorphic rocks give useful stones. Examples are sandstone, limestone, and many others. In the word of classification, we can say one class is clay and silt, which is very dangerous class, while other classes ordinary soils like fine sand, coarse sand, gravels, pebbles, and the third class is rocks, strong rocks. In engineering view, rocks are very good for the purpose of founding buildings, as if rock is free from faults, from weak planes, and from other defects which can be studied. Rock is very good for the purpose of building foundations, as the bearing capacity, safe bearing capacity is very attentive, very good, and settlement is nearly negligible, and economical foundations can be produced on rocks. While soils like sand, fine sand, coarse sand, pebbles, gravel and sand cohesive mix is also very good. If it is well compacted, it can also give very good results on bearing capacity. Whereas clay and silt give very dangerous types of soils, because clay has a very bad property. When it comes in contact with water, it swells, and while water is dried out, it shrinks. Clay's structure is also not very good as far as consideration of engineering is taken up, because the voids in the clay are very high. Voids means it can take air and water, but permeability means flow of water within the clay soil is not reliable, it's not permissible. It can swell many 100%, and it can dry out to shrink. But it doesn't work for the purpose of permeability characteristics, permeability definition, whereas sands are very good for permeability purpose, and rocks is another. Permeability I am talking is, permeable means every soil has voids in its composition, and soil has three composition. Number one is solid soil, voids in that, and voids means it contains air and water particles. So solid plus air plus water particles equal soil. The less the water, the better the soil, because soil has a strength, and voids should be reduced. Water should be taken out from the soil by compaction. So the soil of sand and soil of all types of rocks is very good from compaction viewpoint, because higher the compaction of the strata where the foundation has to rest, better the foundation is, better the bearing capacity is, which is not better for the where the clay is met. Clay strata gives higher degree of settlement, while good compacted sand gives higher compaction and lower settlement. Also, lesser chances of differential settlement in case of rocks and sands. But in case of clay or silt, chances of unequal settlement are much more than other soils. It is therefore very important to note regarding the classifications of soils. It is not simply classification, it is understanding of other properties as well. Because soil should have a defined liquid limit. Clay can have much liquid limit. There should be a good soil which has, means a good soil can take water up to 35%. It should be less actually for a better soil. Higher the liquid limit means lesser the shear strength. Liquid limits, a definition, a virtual definition is, there is a state of soil after mixing of water at which state the soil starts getting shear strength. Means when you go on taking out water from a saturated soil, because saturated soil has no shear strength or very little shear strength. When you go on compacting the soil, water will go on out, will be out, and gradually a stage of water percentage arrives when the soil mass starts getting shear strength, and that is what we call liquid limit. Liquid limit in international codes has been given as 35% maximum for the purpose of good soil, consideration of being classified as good soil. So if the liquid limit is more than 35%, the soil is not respected. But it is very difficult in the field to get 35% of liquid limit in the original soil. So what they do, engineers, they add some other soils, some coarse soils, graded soils to reduce the liquid limit, and they achieve it by many methods, mixing additional soils and compacting. Dune soil, for example, dune sand, it's very fine sand, but it should be clean. This is good for filling up if it's clean and graded. Similarly, another soil is coarse sand, which is river pit sand. That is also very good as sand material because it is coarse and it has permeability. Whereas silt of clay are not good soils for the purpose of founding, building or filling, because clay has many minerals. Those minerals are not favorable for the good crystallization or restructurization of the soil structure, and that is very important. There are three very important minerals in the clay soil, which are one of them is very dangerous, while two are not very dangerous. But generally all the clays contain that one, which is very dangerous. The name I'll tell you later on. There are three. One, Montmorillonite, that is called actually. That is very, very dangerous. While illonite and kaolinite are not that much available and also not very dangerous. But Montmorillonite is very dangerous in clay. If it's available, clay swells to many 100 percentages. It is not acceptable in engineering point. Best thing is, the building is lucky if it gets to be founded on rocks, and particularly if it is igneous rocks, it's very nice. And also if you use aggregates from igneous rocks, it's very good. In Gulf we call them gabbro aggregates, that is from igneous rocks, and there igneous rocks are available near Muscat, while in Qatar igneous rocks are not available, lime rocks are available in whole of Qatar. If you see in India also, rocks are available in certain areas that are igneous, whereas rocks are not available in certain areas. Actually, rock is available in most of the areas if you go much deeper in excavation, but generally buildings are constructed up to 4 meters or 3 meters or 2 meters depth or 1.5 meter depth, which is sandy area in some places, clay area in some places. Yes, clay rock is also available, which is very dense rocks, but that's not reliable because water is available everywhere below the ground at certain depth. That's called water table. And most important thing for foundation soil is that simply soil property is not the final answer. When you explore the soil, you will go below. Even suppose your foundation rests as 2 or 3 meters or 4 meters, but that's not the answer. That's not the final decision. because water flows every time below the, say, 10 meters below the ground level, or 20 meters below the ground level, or 15 meters below the ground level. Water keeps on flowing. Water flows all the way to below the building, below the ground, and it is not visible. But water carries with it many chlorides, many sulfates. Mobility of water, we call it in engineering sense, mobility of water below the buildings, below the foundations. And when this water comes in contact with the soil, if it is clay soil, or if it's sandy soil, or if it is rock, we have to see. If the soil is clay, water will definitely come and work with clay. Clay will swell, it will absorb the water, and due to the porosity of the clay, and this porosity of water will keep, it will keep itself there. It will give the stresses while it will increase the volume. It will give the voluminous increase, that is bulk density will increase, voluminous increase, and that shall give upward pressure. Whereas and also when there is drying, means water is receded, means it drops, and sun works, shrinkage will take place, means you see there's increase in the volume and then decrease in the volume. This is very dangerous. This is to be studied in engineering. Same thing is to be seen for sand. Sand, as we say, sand is porous, of course, but it is permeable. Porosity is very less, permeability is very high. Water keeps on flowing or moving through the voids of the soil. It's very good drainage soil. Means water is not stored in this. That's why sand is good for the purpose of compaction. If water is much below the sand is very useful. But when there is water, there is a danger of below the fine sand. If water is there below during the earthquake, because when there is earthquake and loose sand is there, water is there, what will happen? It will be boiling. There will be liquefaction of the sand below the foundation, and that liquefaction will lose all the shear stresses, shear resistances of the soil, and there will be collapse of the building or failure of the foundation. Clay and silt are equally dangerous, while sand is supported for recommendations. But rock is very good for the purpose of foundation. But if it is igneous rocks and it has good geology with it, means it's free from faults, it is free from folds, it is free from cracks, it's having good crystallization structure, good crystals, no cracks, it's very nice for the purpose of foundations. And we can allow more and more bearing capacity on that, depending on the test results. We can save a lot of money on the foundations, and building can be very durable. Foundations can be very durable. Water danger is over. But there is a problem with the resistance of electricity, etc., because there is a solid. But as far as clay is concerned and silt is concerned, it's not acceptable. But sand is also good for the purpose of foundations, because sand also gives good compacted sand or sandstone, medium density sandstone, high density sandstone or low density sandstone also allows better density and better soil resistance to shear stresses, which is known as bearing capacity of the soil, and also less unequal settlement. That is also recommended for good buildings, as lesser the settlement, better the building, lesser unequal settlement. These considerations of soil, which I have given as a layman in the layman language, are very nice. Now, I'll give you an example of clay soil that is met in one building, that is mine. Here you can see here the soil. This is the pit I have excavated. This is the pit here. You can see the pit, and you can see the soil, how the soil is looking. Soil is giving this all while there's a pit of about 10 feet, 3 meters down here, and you can see the soil. You can see the soil here. This soil, you can see the cracks. This is clay soil. Partly sand is mixed in that, but major portion is clay. You can see this just after the rain. So many cracks are available here. You can see the cracks here in this soil. It's all clay soil. Very dangerous for the foundations. So I cannot allow here foundation on this bed. but we have to apply soil improvement on this bed. You can see the structure here. Very well, means it's a practical. I'm showing to you, completely practical. You can see this is soil. This is the pit here. And the soil here. You can see the soil here, cracks here, you can see. This soil is not at all good for engineering purpose. And because I have to take the building down 2-3 meters because to accommodate the basement, the foundations cannot be rested on this soil. So I have decided to take out below 30 to 50 centimeter of bad soil, clay soil, from the foundation's whole area and replace by the graded sand or desert fill or gravel fill, anything that shall work for the purpose of providing 10 to 15 tons per square meter of safe bearing capacity. This clay soil is not the answer to the building designs, and it's also available in many states, and particularly in our country, Bharat. In some states, it's known as black cotton soil. The color is black there, and that is also clay. You can see this is clay. I will give you a very, very clear glimpse of the clay. This is really, but here in this locality I have seen all people are using this directly without any soil improvement, which is not recommended in engineering studies of soil. And this is what it is. It's not acceptable. The purpose is to tell you how it works. Soil investigation is very important. It's not simply theoretical study. One should have practical study. You can see this pit. It is straight vertically. Means there is no fall. There is no angle of approach in this, 90 degrees actually. And this has been there for a few months. And soil is caving out. You see the soil is caving out? This is what it is. It's caving out. At many locations I have seen, it's caving out. This caving out, this clearly tells that soil is very weak in shear. It cannot take shear, and that is the reason it's very weak to give the ultimate bearing capacity. It's not giving that. Even without testing, we can understand. So I have recommended to improve the soil by replacing the bad soil, by the good one, by the graded aggregates, or by desert fill or any other means. I have seen on many projects in Middle East that generally in certain countries good soil, good rocks are available. For example, in Qatar I have seen rocky area is extensive. I have seen rocks there, lime rocks, and somewhere very hard rocks. And all excavation is done there by rock breakers. Whereas in Iraq, I have seen generally the soil is clay and silty. On whatever project I worked, I saw all such types of soils. And excavation was very easy there, but dewatering problem existed everywhere. Similarly, in UAE, I have seen sandy soils because of sandy nature of the soil, seashore and dunes. All soils are there, such as the field lands claimed area, actually reclaimed areas. What they do, there we have to provide soil improvement everywhere in most of the places, and soil improvement is very important. Soil improvement is done by replacing the bad soil, taking out the bad soil and replacing with good soil. Also by inserting certain sand columns or certain piles are to be provided. Sand columns is very good answer nowadays in the modern world. Sand columns are inserted into the bed base and the strength of the base is increased. Similarly, somewhere they provide the piles even for the smaller buildings, less height building, and these piles go to the hard stratum below. It may be hard rock or it may be hard stratum. These are the only simple solutions for improving the bearing capacity of the soil. Sometimes it is very difficult to take a judicious solution, to find judicious solutions for the foundations because of restrictions of the budget. But budget is second criteria here. First criteria is safety. As far as possible, RCC foundations are considered the best, and if the soil is weak, it is better to provide raft, mat foundation, or if building is too high, mat foundations in combination with piling. If the building is of different nature, it's also better to provide continuous beams, raft. You can say beams frame in place of raft. Beams not like as I step, but different type of beams, frames connecting all the columns in both directions and considering the beam. And when these beams are worked by the horizontal forces such as chisel action, these beams are automatically converted to columns in service, and that is very important to dampen the forces of earthquake. It's just a preliminary discussion. It's not the final one, but to provide information to the public, I have just brought to you certain effects. If you take the soil below the seas, these are all black in color basalts, we call them. And it's better if your building foundation is rested on a good soil, good base, so that it is stronger, less material is required, more services given, more services offered by the foundation, and building remains stable, durable, while the weak base always poses a danger for the unequal settlement of the building, and due to the caused unequal settlement, there are chances that the building can fail any time in future during surveys without giving any warning.